Okay, welcome everybody who's watching, and great that you join us tonight to witness this year's final of the Van Swinderen Prize competition. A special welcome, of course, for today's four competitors, the recently cum laude awarded doctors Bjorn Kriete, Ella Beckhuis, Hero Banco, Piano and Tom Burke, and also for the three members of the expert jury. A special welcome, of course, for today's four competitors, the recently cum laude awarded doctors Bjorn. The present, and also a special welcome for the members of the expert jury, the professors Erik Boddeke, Henk Broer, and Theo Elzinga. The present 1839th meeting of our Royal Society for Natural Sciences is for the first time a completely online edition. This is an interesting and, as a result of the present corona restrictions, also necessary experiment, but I'm confident that all preparations will work out fine and that we will have an enjoyable and exciting evening. The prize is named after Theodorus van Swinderen, who as a student started our society in 1801, almost 220 years ago. The competition for this prize was organized for the first time exactly 30 years ago, so tonight we are part of quite a long tradition. For the contestants, it's good to know that in addition to the great honor of winning this prestigious prize, there's also a lot of money attached to it. €2,500 for the winner of the public prize, with €1,000 for each of the other three finalists. On top of that, we have the expert jury prize of an additional €1,000. So there's a lot at stake tonight. As you have seen, we have a tight schedule tonight, so without further ado, it is my pleasant duty to give the virtual floor to Professor Theo Elzinga, who as chairman of the expert jury will enlighten us about the procedure of this year's Van Swinderen Prize competition. Theo, the floor is yours.
Thank you, Lou. The jury was very pleasantly surprised with the quality of all the summaries of the different theses of the candidates that all have received a cum laude for both the writing of the thesis and the thesis defense. But of course, it was all about the summary. And although it gave us all three of the jury members several hours of pleasant reading, often on topics that we are not the experts in. But apart from being pleasurable, it was also work. The three members of the jury each independently made a ranking of the candidates, and they did that roughly on the following criteria. We looked at the composition, whether it was well thought through or whether it was just following the flow of the different chapters. The composition is a very structural part of the whole summary, and we expected a little bit of our cum laude candidates, a little bit of elaboration on that structure. We also looked at whether they succeeded in explaining the work that they presented in a scientific way in the thesis itself, in a way that was also accessible to layperson, for non-experts. And that often proved to be outside of the comfort zone of most of the PhD thesis summaries. But the candidates that we have selected all succeeded in at least convincing us that the summary was on a thesis that was also interesting for the non-specialist. It should also be captivating or stimulating. So that had been done in very different ways, in pointing out the scientific relevance or just the sheer fun of solving really difficult questions on purely scientific grounds. And then we had the fourth category, and that included strengths and weaknesses not covered by the above three criteria. So based on all our individual rankings, we combined our lists, and although there was quite some spread in the different lists of candidates, we agreed on these four, which we thought were all excellent, and in at least at least two of our individual rankings ended up in the top. So already there is a justification for at least €1,000 prize winning money for each of you. And now you enter into the competition of winning also the Publix prize. Okay, so in completely random order, not alphabetic, not on basis of the ranking that we have established, we would like to introduce to the public Björn Kriete with a thesis, exciton dynamics in self-assembled molecular nanotubes. And I give the word to the expert himself.
Thank you, Chairman, for the kind introduction. Tonight it is indeed my great pleasure to introduce you to my PhD research that I conducted at the University of Groningen between 2015 and finished this year in 2020, actually also digitally back then. So before I take you along and we dive together into my research topic, I would like to take a brief moment to thank the organizing committee for, first of all, this unique opportunity, and then second of all, of course, for the nomination for this year's Van Swinderen Prize. So as you can see, the official title of my talk is Exciton Dynamics in Self-Assembled Molecular Nanotubes, which I think is a pretty scary title. So on occasion of today's talk, I adopted a different and somewhat, I think, more intuitive title, namely Bio-Inspired Antennas for Light-Driven Applications. And so in my presentation today, I will take you along. I will explain what bio-inspired antennas are, how they are made, and of course, what they are ultimately good for. So bio-inspiration, what does it mean? I mean, from a very general perspective, it means observing an effect in nature. It may be quite obvious, but it also may be quite subtle, as we will see. And then try to mimic this effect for technology or for technological purposes. Still might sound a bit abstract, but bear with me because, of course, I have prepared a few examples. Take, for instance, this guy, a lizard. And maybe you've wondered in the past how he or she is able to climb magically up vertical walls. Well, scientists have wondered the exact same question. And in fact, the structure of the feet of the lizard has inspired materials for dry adhesion, meaning that it is a nanopattern surface that sticks to another surface without the need to apply any additional glue. A second and maybe even more prominent example is the lotus effect, where droplets of water simply roll off the leaf of a lotus and then are collected somewhere further down. This effect in turn has inspired coatings for solar cells, which have the same effect and keep the surface of the solar cell clean. And this way they greatly help with the maintenance of solar cells, keeping them clean and nicely efficient. So these are two examples where we have successfully learned something from nature, but there's also one where I'm wondering if we can learn more, and that is photosynthesis. So in times of ever-growing energy demands, the need of sustainable energy concepts is also growing rapidly. So photosynthesis in that regard is a very promising candidate to look at because it can be considered Earth's powerhouse, simply because the total amount of energy that it captures and utilizes outcompetes the total amount of energy that humankind needs by an order of magnitude. So by looking at photosynthesis, and learning from it, can we actually extract some valuable design blueprints to enhance current technologies, as for example, our solar cells, or even spawn entirely new technologies? At this stage, you still may be a bit skeptical and wonder, well, how is nature even ahead of us? After all, we cannot simply wire up a leaf to power our electric car, our electric bike, let alone a meager LED. So, for starters, nature actually has had a bit of a head start of some billions of years to do quite some optimization, some learning by doing. In comparison, the solar cells that we have only look back at 180 years of optimization, and that is actually adopting a very optimistic view dating back to the discovery of the photoelectric effect. So what has this optimization yielded? In what aspects do the natural systems outperform our precious technology? When you think about technology, then you perhaps think about people working in clean rooms in these kind of suits, for example, here at the University of Groningen or at my current employer, ASML. And the purpose of the clean room is, of course, to have very well-defined conditions and a very clean environment, which is absolutely instrumental for the silicon industry, for example, on which the chip making industry is based on, or also the solar cells. So all in all, what you need to manufacture these is extremely clean conditions. You have to have extremely stable temperature. You need dry atmosphere, or in some cases even vacuum, which makes it even more complicated. And not complying with the list of these requirements, the penalty for that is actually quite harsh, because the final product is not going to work as intended, as you would like it to. By contrast, when we look at nature, this is not exactly what we would call very clean. You also have a not very well-defined environment. It's humid, the temperature is constantly changing, not so much in the Netherlands where it's constantly cold, but all in all, you have ever-changing conditions. Nevertheless, the natural systems that I was talking about, they don't really seem to care about these conditions. So they're very robust, and they just do what they were designed to do, namely photosynthesis. So how is that possible? To answer that, we have to zoom in a bit. So nature achieves that actually by employing tiny machines, namely light harvesting antennas, as I plot them here, which consist of a tight network. And well, these are really small. So one of these antenna networks measures only about tens to hundreds of nanometer, which is a tenth or a hundredth of a millionth of a meter. Well, this is an inconceivably small number, and it's quite hard to imagine. So I tried to find something to translate to that to, and something that we can all relate to currently. And as it happens to be the case, this whole thing is about the size of a coronavirus, so really small. What these antennas do is quite literally what you would expect them to do. They capture sunlight, the incoming sunlight, and then they transport the energy that they have captured to its destination. And in that case, the destination is the so-called reaction center, which uses the energy in order to perform photosynthesis. So this way, the light absorption is maximized, the energy transport is directed to where it's needed, and because it is such a tight network, it is quite robust against external disturbances. How well are these working, you may ask? Well, some photosynthetic systems, as for example, these green sulfur bacteria that are shown here, are known to perform photosynthesis in extremely light depleted environments. So this is down to only 1% of full moon light, which is extremely low. And at these levels, you cannot really afford to lose any of the energy that you capture and then just lose it again, because you really need it to do this. So the question arises, how can we now combine the best of both worlds. How can we come up with new functional materials that will allow us to enhance current technologies or come up with entirely new? What we have done in the first place, and the first step, is to extract some design blueprints. What we have come up with is basically a wish list towards an artificial material, and this way basically made ourselves a cooking recipe, which, if we now set out to make an artificial analog that we can use for technology, has to comply with. So we, in principle, just need to check all the boxes. So how to make these? For that, it is, you start with individual building blocks, molecules in most cases, you let them interact, and then you may end up with, well, they may form chunks, bigger, smaller, none. But the important bit here is that you get no network. And because you have no network, you also have no energy transport. So that definitely doesn't check our main box. The problem here is that there is no guiding motive. Well, instead of using these ordinary building blocks, we can use smart building blocks, which were chemically engineered. And this way we imprint a roadmap how we want them to self-organize. And this way they organize into a nicely ordered network. The most amazing part here is that you can actually see by eye the changes that were taking place, which then is the picture that I showed on my opening slide, where the network actually interacts very differently with light, and that is what we wanted to, right? Than the individual building blocks. More importantly, because it is a network, it is also robust against disturbances. So, example, I remove one of these bricks. Well, the energy transport doesn't care because it can just simply go around. Well, I think by now I have built up the suspension far enough to finally show you what these antennas really look like. And that is them, the artificial light harvesting nanotubes that I was investigating in my PhD research. You can see that, well, they are pretty tiny. You have to magnify them by 70,000 times. And still, then that means they are about 10,000 times thinner than a human hair. You can also see that they are wire-like structures that, well, as we saw on the previous slide, strongly absorb with light. The important bit is that, well, because they are wire-like, they can absorb at some point and then transport the energy to wherever it's needed. So, of course, the job is not 100% done at this point, because much of my PhD was actually this iterative process, because taking these as given is not enough. You also have to modify, test them, optimize them, change them, and adapt them. And this needs a quite, well, a multidisciplinary approach, because only by basically approaching the same problem from multiple angles and then combining all these angles into one coherent picture, where I'm talking about techniques like ultra-fast time-resolved spectroscopy, microfluidics, cryo-TM, simulation, single object microscopy, and all of these you have to combine into one coherent picture to really get insights into their true properties. So most of these techniques meant that I had to spend countless hours of my PhD holed into the pitch black darkness of a laser laboratory. But luckily, it also meant that I could quite literally shed light on the true properties and the great potential of these systems. So when you remember this talk, then I would like you to remember these artificial light harvesting nanotubes as energy highways, basically as a great way to come from point A to point B, unless you have to commute in the Eindhoven area where I now live. And so as these highways, these actually have multiple lanes available. Great, makes the transport more efficient. They also can avoid congestions by automatically adjusting to the illumination conditions that we put them under. They are indeed robust to disturbances, so just think about road maintenance. And in fact, this is the kind of road maintenance that does not disturb the energy traffic. We really try to destroy them. They are really resilient to do that. And finally, I've also found a recipe how to tune their properties, how to basically change their infrastructure. So the energy can then be transported along, and depending on what you, along these wires, and depending on what you hook it up with, then you could use that basically to fuel applications that utilize sunlight, for example, for the generation of solar fuels. Hydrogen is a very big topic right now, or to enhance the energy transport in photovoltaics and solar cells, or as a third and very relevant topic for the University of Groningen, maybe at some point to power molecular motors. This concludes actually my presentation, and therefore I would like to acknowledge funding from the Zernike Institute for Advanced Materials, and also for embracing lots and lots of collaboration. So I had the joy of working with a lot of different people with lots of different backgrounds during my PhD, for which I'm extremely grateful, and also from which my thesis has greatly benefited. Finally, if I tickled your interest and you would like to know more about the juicy details about all the experiments that I did, I cordially invite you to check out my PhD thesis. And with that, I would like to thank you for your kind attention. Please stay healthy, and I wish you very pleasant holidays quite soon. Thank you very much.
Okay, thank you very much, Björn, for your very clear explanation of your thesis work, and also sticking to the allocated time almost to the second. So also praise for that. So we go to our second selected candidate, Ella Beckhuis, and she wrote a thesis which was called A Body-Mind Map, and then a long subtitle. And I just ask you to not only mention the subtitle, but explain the whole thesis work in your presentation. Please, Ella, go ahead. Ella, can you check your microphone?
I'm sorry, I was muted. I'll start again. Good evening, everybody. My thesis is about the relation between depressive anxiety and somatic symptoms. And in the next 15 minutes, I would like to guide you through the body-mind map, as I have explored in this thesis. And that relation between the body and the mind is one that has puzzled many physicians. And as a resident in psychiatry, I was therefore intrigued by that relation, and I decided to focus my research on that relation, and in particular on the relation between those depressive anxiety and somatic symptoms. And here we are looking at the cover of my thesis, which shows how complex that relation between the body and the mind is. But it also represents an actual map, not just the body-mind map, but an actual map of the place where I grew up, which is this village over here called Millingen aan de Rijn. And as the name suggests, that village is situated next to the Rhine River, just on the German border where the river enters our country. I chose this picture because the Rhine River was very central in my youth. I grew up as the daughter of the keeper of the nature reserve here around the Rhine River. That meant that I often played in the water and the sand of the Rhine as a child. But it also meant that we had to watch out for the water because the area where we lived is an uiterwaard in Dutch, which means that it is situated rather low in order for the Rhine to be able to flood that area in case it is high water, which happened about every year. So here in the upper right corner, you see the road to our house back then, which in case of high water could be set underwater. And then we had to evacuate, which happened quite a few times. So during those high water times, we were anxiously watching the water levels of the Rhine and to see if the water would cross the threshold of the road to our house would be set underwater, because then we had to pack our bags and leave. Now, and once I started doing research, I realized that the way that we look at depressive anxiety and somatic symptoms in research actually resembles the way that we checked those water levels back then. Because when we assess these symptoms in research, we ask a patient if he has several different symptoms and if he can score them based on, for instance, their severity. And those scores are then all summed up to one general sum score. And once that sum score reaches a certain threshold, we assume that that person has a depression or an anxiety disorder or a somatic symptom disorder. Now, but the way that we check those water levels when I was a child is not representative of that massive Rhine River, right? Because the Rhine comes from very different sources in different countries, which then come together, and together they form the massive Rhine River. And it is the same with these sum scores. They consist of various different symptoms, which are likely to have different causes, different consequences. If we take a look at the depressive symptoms in the middle, for instance, feeling down is not the same as sleeping problems or concentration problems or feeling guilty, right? But still we treat them the same in these sum scores. And these symptoms are also likely to influence each other. And now, why is that important? Because individual patients have different symptom profiles, and these symptoms are likely to interact in different ways. For instance, these two patients, the first patient started with muscle pain. Because of the pain, he started to feel down. And these depressed feelings interfered with his work, and therefore he started getting anxious about what might happen to his future career. Another patient felt dizzy often. Because of that, he couldn't spend as much time with his children as he wanted, felt guilty because of that. And because those feelings of guilt were so overwhelming, he developed panic attacks. So we have two different patients with a completely different story, but still we treat them the same because they have the same score on their sum scores. Now, in this thesis, we therefore wanted to focus on individual symptoms and their characteristics in order to be able to translate our findings better to the situation of individual patients and their specific symptom profiles. And I would like to tell you tonight about two projects. One is about the epidemiological characteristics of these individual symptoms, which is about how they occur in the population. And the second is about the clinical characteristics, which is about how they behave during treatment. First of all, the epidemiological characteristics of individual symptoms. We wanted to get a grip on how symptoms related to each other in the population. So which symptoms often go together and which symptoms maybe don't. And we used a sample of nearly 3,000 persons for that from the Nesta database, most of whom had a depressive or anxiety disorder. And we assessed 30 individual depressive anxiety and somatic symptoms. We use network analyses, which is a novel type of analysis that shows how these symptoms are interrelated. And it shows it in a kind of map, hence the title of my thesis, a body-mind map. And here you see that map. And in the circles, the individual symptoms are displayed. And the green lines between them show the symptoms that are associated with each other. And those associations indicate that if a person has one symptom, he's also more likely to experience that other symptom. In gray are the depressive and anxiety symptoms, and in black are the somatic symptoms. And from this map, it becomes apparent that not only depressive and anxiety symptoms are strongly related to those somatic symptoms, but also that these relations are strongly dependent on the type of symptom. Each symptom shows a unique set of associations to that other domain. For instance, this symptom, anxiety, shows many associations to the somatic domain, like to excessive perspiration, to pressure on the chest, to breathlessness, to pain on the chest, etc. But other depressive and anxiety symptoms, like your hypersomnia, was not related to somatic symptoms at all. And that shows us that in the relation between these symptoms, some symptoms are more important than others, and they might be an interesting topic for further research, or maybe even interesting targets for treatments. Then we move on to the clinical characteristics of the symptoms. And we did that by investigating how the symptoms responded to a treatment. We used a randomized controlled trial of nearly 200 patients who had a depressive disorder. And half of them received a form of psychotherapy alone. And the other half received that form of psychotherapy combined with antidepressants. And we assessed 16 individual symptoms and we explored how they responded to that addition of antidepressants to psychotherapy with network analyses. Again, in the circles are the individual symptoms, and the green lines indicate if they are associated with each other. And now here appears the treatment variable, which shows the effect of adding antidepressants to psychotherapy. And that addition appeared to have effect only on particular symptoms and not others. It had, for instance, a strong effect on feeling entrapped and emotional ability, weak effects on worry, hopelessness, and low in energy. But other symptoms did not respond to adding antidepressants at all, like feelings of worthlessness, thoughts of the death, concentration problems. So that indicates that adding antidepressants is beneficial for particular symptoms, and so also only for patients who have those particular symptoms. From this research, we concluded that individual depressive, anxiety, and somatic symptoms each have their unique characteristics, both in terms of epidemiology and in their clinical setting. And that indicates that if you combine them all to one sum score, important characteristics are obfuscated. And in order to get more grip on how individual patients develop their particular symptom profile and how those symptom profiles can best be treated, we need to know more about these individual characteristics, because with these results, we can eventually allocate patients to different treatments based on which symptom profiles they have, maybe. We started this presentation with the map of the Rhine River. Well, and that was complex on its own, but there are so many more rivers to explore, and so many more symptom types and how they behave in such networks. And I hope that you have become just as curious as I am about how these symptoms behave, because the symptoms of individual patients do not stick to the boundaries of disorders as we have named them. So it would be very interesting to get more a better idea of the characteristics of symptoms in general. I would like to thank all the people who have contributed to this work. And of course, I would like to thank the KNG for giving this opportunity to present the work to you. I hope you enjoy the rest of the evening, and thank you for the attention.
Okay, thank you, Ella. George, I realized that I spoke out of turn and that it was your job to introduce the presentation.
But you can continue, Theo. So
Okay,
continue. I do the voting.
Okay, that's great. Okay, we are already on to our third presentation, and that is by Herip Blanco Reaño, hydrogen potential in the future of EU energy systems. Very societally relevant and definitely for the northern provinces. So Herip, the floor is yours.
Give me 1 second while I set up this, and hopefully this doesn't count as my time. 1 second. Yep. So good evening, everyone. Thanks a lot for making the time. As you can see, I've tried to make it as live as possible. Sorry, give me 1 second. In this COVID-19 times, sorry. Hopefully, again, this is not part of my time, and just takes 10 seconds. So again, thanks everyone for making the time. Again, as live as possible as it can be. A bit of context on this thesis is that it is an engineering approach. It's focused on the energy system, looking at 2050 scenarios and the potential role that hydrogen can have in such a future. So I thought I would start with a common point that we might have. You might see in the news global warming, temperature rise. So here what I'm showing you is the relationship between CO2 emissions and global temperature rise. We have already locked in around 1.1 to 1.2 degrees Celsius. And basically we have limited room for further CO2 emissions. It has been proven that most of these CO2 emissions are from human activity. So we have to do something about it. Consequences of that higher temperature are, well, changing precipitation patterns, heat waves, sea level rise that ultimately affect society, things like income, economic growth, population displacement, and energy consumption. So at the end is a lot of this increase in CO2 emissions has been due to human activity, and we need to do something about it. So according to science, we need to go from where we are today, around 33 gigatons of CO2, to net zero by 2050. And then we have a set of technologies available for that. But what I want to highlight here, well, you don't need to know what each technology is. What I want to highlight here is that each of those options has its own challenges. So none of the options, but on their own, will be able to get us to where we need net zero by 2050. So that's precisely where hydrogen, which I focus on, comes in. Hydrogen is one more technology in that portfolio that in many ways complements the technologies and some of the challenges that those have, and basically adds more flexibility to that portfolio. It adds one more option to reach that net zero and increases the chances of us getting there. So that's what leads me to the main problem that I address, which is what role can hydrogen have in such a future low carbon system? Now role, you might define it very different ways, but since this is again engineering approach. It's basically, so it's looking at energy balance. So things like what capacity of wind and solar do we need? Where do we need those capacities? Looking at the downstream uses and seeing, for example, how does hydrogen compare with electricity, biofuels, other energy carriers, and all the end uses in the energy system. So that's one aspect of energy balance, capacities, and flows. Another aspect is the cost. How much does it cost? What's the effect on energy prices? What investments do we need? And the other aspect is the environmental impact. But at the end, it's not about the numbers. It's about how do they translate into action? How do those inform policy making? That at the end is what it affects the actual societal change. The other part of the question is future. That's in this case is 2050. So you might say, well, we use a crystal ball, place ourselves 30 years from now, and then know what we have to do today. But since this is science-based, it's based on a model and scenarios. Scenarios to make sure the decisions that we make are robust to those potential futures. And then for the model part, an analogy here that I want to make is, if I show you this picture and ask you where I am, you might say, well, you see some water, that could be a lake, that could be a river, maybe you say Lake Geneva as an example. I give you this piece of information, you pretty much see that's a cloud and sky, you cannot tell much more. If I show you this picture, you at least know this is not the Netherlands because it has a mountain, but it doesn't tell you much more than that. And this picture also doesn't tell you much. What I wanna, but the point I'm trying to make here is that each of these pictures on their own doesn't give you the answer that you're looking for. And it's only when you put the pieces together that you're able to have all the information that you need and make an informed decision about, in this case, where I was. The analogy here with the work I did, and here already the reference and making the jump to the work that I made. Here on the top, you see 8 different pictures that an ideal model for hydrogen would have. This so far had not been identified, so that was part of my work. And then here on the left, you see different models that could be used to model hydrogen. And again, those had been used for things before, but not in this integrated manner. And the same as the picture that I showed you before, where no single picture had the answer, here's the same. No single model covers all the features that you need for hydrogen. Yeah, so they're incomplete on their own, but you do see that this energy model in the bottom does cover 4 of the 8 features. And you might think, well, if you take this energy model as a base and then combine it with a couple of others, you're basically covering the entire spectrum. And that's precisely what I did. But so far, this is the before. Those models have been used for single countries, for in single models with inconsistent data behind them in terms of cost and efficiency, for example, and limited number of scenarios, which give you limited insights. So what I did was to integrate those in what I call an integrated framework, where those pieces are together. And then the so-called energy model that you saw in the previous slide, which was the most complete based on cost optimization, that was the core of the work, complemented by the other models that you see there to cover for some of the gaps of the energy model. So that integrated views was one of the state-of-the-art features of this model. It was also European-wide. Before, a lot of the models were single countries. This was for the European Union as a whole. The other one is that this looked beyond hydrogen, also hydrogen derivatives. And I also did over 100 scenarios that allow you to see trends rather than limited insights from each. So you might say, why going for all this trouble and making this coupling of models? It sounds so complex. So I've tried to simplify the why for this by taking a specific scenario, a specific example. So we're looking here at a passenger cars, the mix, the type of cars that we have in one scenario. And then we see, well, electric vehicles is most of it. There are 1/3 of hydrogen vehicles. And then this is the price tag. This is the result from this so-called energy model. which is based on cost optimization. So you might expect this is the lowest cost. Once you couple it with the other model, one behavioral model, you see that the mix looks pretty different. Now, electric vehicles are 1/3. Suddenly there's hybrid vehicles, and the cost is 14% higher. So the point is, it's really different. You might say, why going for the higher price tag if you have a lower cost? Because in reality, our decisions for cars, we don't make them only on cost, right? We make them based on income, on brand, environmental performance, safety, and among others. So these are features that the cost optimization was not capturing, but you do capture it once you extend it and couple the model with the behavioral model. So the point here is coupling the models makes a difference in the results, makes a difference for the hydrogen demand, which is ultimately what I was looking for. Now, another quick example here is from looking at the environmental impact. And again, this is a selected example of taking one specific part of the work. These are CO2 emissions from a specific scenario. And then you see the energy model reaches the blue line, which is the target, 95% CO2 reduction. But the so-called energy model only considers combustion emissions. Once you add up the life cycle emissions, and those are, I take as an example from electricity to hydrogen, you see there are emissions in the construction of the wind turbines, in the construction of the power lines, and so on, car manufacturing. So all of those emissions add up, and it's basically all the bars that you see here stacked up, and you see that it changes from basically this level only the green, it almost is 4 times higher once you add up the life cycle emissions. So the point I'm trying to make here, this changes the emissions, this changes the hydrogen demand, which is ultimately what we were looking for. Now I could continue with the same approach and tell you, well, this is the answer to the question that I made of hydrogen demand. We're looking at supply, demand, different scenarios. I could tell you this is the price elasticity, willingness to pay of different sectors, a nice figure with energy, the supply and demand, and the role that hydrogen plays in all that, or the powertrain mix for a certain scenario. But at the end, it is not about those numbers, but it's about the insights that you can take from those numbers by taking a step back. So I've selected a couple, 3 insights to share with you from all those numbers. Insight number 1 is that hydrogen will be needed, but other alternatives come first. Using the same figure that I showed before and the pathway to net zero in 30 years, my research, and it's also in agreement with research by international organizations, show that, well, energy efficiency, renewable energy, and electrification are 3 of the key measures, key alternatives to reach that goal. But they will only get you so far. To really get the last 10, 20%, you really need hydrogen for that last 10, 20%, along other alternatives that you see there. So you might ask yourself, well, if we need it for that last 20%, 10, 20%, why not waiting then for 2040? Well, the answer is because we need to have the technology ready. We need to make the investment today. We need to have the governance and policy system in place, the market design, to make sure everything is ready for when it's needed by the system. So that's insight number 1. Second insight is that there are some specific end uses where hydrogen is needed the most. So I could show you this picture, and well, this is basically where hydrogen can be used in the system and anywhere, actually, like electricity, and it could even be more complex than that. But at the end, you don't really need all those uses. Again, from as far of the modeling output, this is one insight, that first, the one with highest priority is industrial feedstock, where you use hydrogen today and then change that hydrogen from high carbon intensity to low carbon intensity. Second use would be for aviation that requires a higher energy density, and then basically it's either biofuels or synthetic fuels from hydrogen. Shipping, it's either hydrogen or ammonia, which is a derivative. Steel also has limited options, carbon capture, store, or hydrogen. And once you get to this level, it's a blurry picture already. It's not a clear cut, if you need hydrogen or if the solution is something else. So the point I want to make here is, well, focus your efforts and on the priorities. These 4 sectors go first. Have some research and efforts on these 2 sectors, and the rest are really for the longer term for some very niche applications. Third insight is that hydrogen derivatives should also be considered. You could start from hydrogen, you combine it with carbon dioxide from air and nitrogen from air as well to produce syngas and ammonia. And once you're at that level, you pretty much can cover the basic needs of different sectors, things like ships, aviation, and industry, for example. But once you have that level as well, you could produce chemical feedstock and make sure the feedstock for the industry, it's also green. Sorry, someone was chatting. Sorry for that. So make sure the feedstock is for that industry is also green and exploit the hydrogen potential. Now, why do I select this as an insight? Because a lot of the government plans, announcements, industry efforts are focused on hydrogen only. But to really exploit the potential for hydrogen, you have to look beyond that molecule and combine it again with basically what you see here in the picture to make sure you exploit the green or renewable electrons to the conversion to molecules. So you might say, yeah, so what do I do with this insight? What's the real impact? Where do they end up? So I might show you in terms of impact, different journals, they have certain impact factor, and then that's a measurement of impact. But at the end, where I made a difference here is that, yeah, I didn't do this by myself in a room in the university, crunching numbers. I did this, I was 2 years at the Joint Research Center, which is the research body of the European Commission, and then directly feeding into the policymaking process for the European Union. I was 6 months in the International Energy Agency, which is an intergovernmental organization giving advice to countries, mostly G20, on energy matters. And there I wrote with some colleagues the Future of Hydrogen report, which is until today highly quoted by government, industry, and research institutions. The model, 2 of the models that I use are now open and can be used for further research. Some of the scenarios from the work ended up on IPCC, which is a part of the UN, part of the United Nations looking at climate scenarios. And at the end, all of this work is what allowed me to be also where I am today, which is another intergovernmental organization, specifically on renewables, giving advice to governments, mostly in developing countries, on actions to promote hydrogen. And at the end, as a closing remark, I would say it's not even about policymaking, it's about our daily choices, and we need everyone if we are to make this change. Thank you.
Thank you, Ariep. A very clear presentation on the potential of and the necessity to utilize hydrogen. And that brings us already to our final presenter, that's Tom Buurke. We're happy to have a nice balance between the medical faculty and the science and engineering faculty. And so we're back in the medical faculty with Tom Buurke's thesis, Adaptive Control of Dynamic Balance in Human Walking. Tom, the floor is yours.
Okay, thank you for the introduction. Tonight, ladies and gentlemen, I'd like to tell you all about balance control during human walking. And to explain the topic to you, I'd like to start with walking animals. Because almost all mammals on planet Earth walk on 4 legs. It makes for a very easy and very balanced gait. Because if you're standing on 4 legs, it will be very hard to be pushed over. However, humans are special because humans walk on 2 legs. And in the early ages of evolution, this gave us the ability to use our hands to do other things, such as develop tools and, for instance, hold a spear while we were hunting for food. Now, in modern days, this walking on 2 legs is even more important, as we can now tip off our heads or send a WhatsApp message while walking on the street. However, while this walking on 2 legs may be great, it comes with a downside. Because to walk on 2 legs, we need control of our balance. Because we are actually keeping a 2-legged system upright. And if you look at this picture of a chair over here, I think you'd agree with me that if you'd have to balance this chair on 2 legs, it would be very hard, and it would only need a small touch for it to tip over. Now, luckily, humans have a musculoskeletal system, which consists of bones that prevent our body from collapsing, and we've got muscles that we can contract to get those bones moving. And with this musculoskeletal system, we're able to keep our balance during walking, and we're actually quite good at this, because we can say that this balance control during walking is adaptive, which means that it is flexible in changing circumstances. And to stay within the theme of the Van Swinderen Prize tonight, I'd like you to consider a PhD defense in Groningen. So as you walk to the Academy building, you cross the cobbles of the Broerstraat, you walk up a flight of stairs into the main hall, up another flight of stairs and onto the carpet of the aula in the Academy building. And you do all that without falling over, of course, but also without even thinking about the steps you made. And this is great because we don't have to think about it, but we're extremely flexible until we lose control of our balance. For instance, with natural aging, disease, or in an earlier age after an injury or sports injury, all of a sudden we lose the ability to control our balance during walking, and we realize how easy this once was. And with that, you lose the ability to do an easy task, such as go out to shop for some groceries. And because of that, losing the ability to walk can lead to social isolation and can lead to great decrease in quality of life. So what we want to do is increase balance control for people who've lost it. And to do that, we first need to understand how we control our balance. And since this is the Royal Society of Natural Sciences, we've got a mechanical model for this. And I'd like you to consider human walking like a falling inverted pendulum. Now, if you consider the stance leg during walking, so the leg you stand on over here as an inverted pendulum, the body's center of mass, so all the body weight is modeled on top of this inverted pendulum. And as you push off, you propel this inverted pendulum forwards, and it tips over and falls forward again. You catch this falling movement with your next step, and this is the new inverted pendulum. There's forward energy left in the system, and like that, we get another forward falling motion. And like that, human walking is actually like a series of falls, but we're capable of preventing the next fall just in time by making a next step. Now, if this pendulum falls forwards, it will also fall to the side, and therefore we make our steps slightly outward to also prevent ourselves from falling sideward. Now, research has shown that for forward balance control, we do not need to actively control where we place our steps. So you can roughly place them somewhere in front of you and you'll be fine. However, for sideward balance control, mediolateral balance control, you need to actively decide where you place your steps, as placing them too far outward will make you lose energy, and placing them too far inward will make you lose your balance. Now, the current leading theory on control of mediolateral balance has been developed here in Groningen by KNG member Ad Hoff and colleagues in 2005. And they came up with the concept of the extrapolated center of mass. Now, if you consider the body center of mass again, shown here at A, Hoff and colleagues found that you also have to include the velocity of the center of mass, so the speed. Because when we're walking, we're talking of a moving body. This body has a certain speed, this mass has a certain speed, and you have to include that in your calculation of balance. And if you do that, you get the extrapolated center of mass projected onto the floor here at B. And their theory says that as long as you keep your extrapolated center of mass at B, within your base of support at C, and your base of support in walking will be your feet. So as long as you keep B within C, you'll have a stable gait. And you can quantify this relationship for balance control by a spatial distance between the extrapolated center of mass at B and your feet or the base of support at C. And this is our measure of balance control. And while this has inspired a huge amount of balance-related research in the fields of biomechanics, human movement science, and rehabilitation science, we're not actually sure whether we adapt the margin of stability. And like I said before, this adaptive capacity is what makes human walking and human balance control so great. Now, to assess this adaptive capacity, we have a split belt treadmill here at the Department of Human Movement Sciences in the UMCG. And it's shown over here. And in this picture, you can see that this treadmill has two belts. So unlike a regular treadmill with just one belt, There's a small gap in between, and we ask our participants to place the left foot on the left belt and the right foot on the right belt. And we can control the speed of these two belts independently. So we can speed up the speed of the left belt to say 3 times the speed of the right belt. And that's exactly what we'll do. So we have a group of healthy participants and we let them walk faster with one leg than the other, which is an awfully weird task. And as you can see in the bottom video, our participant struggles to keep her balance while performing this task. What you should also note in the top video, in the sagittal plane, is that her left steps are a lot longer than her right steps. So there's a large left step and a small right step. And we call this an asymmetry of step length. So by walking on a split belt treadmill, you get an asymmetry of step length and you have trouble to control your balance. But like I said, humans are very capable of adapting their walking motion. And even though our participant has never done this before and didn't receive any training or instruction while doing this task, after 10 minutes of split belt walking, her walking pattern now looks like this. You can see that there's no longer a problem with balance and that her step lengths became more equal. So we say that the step lengths have adapted to split belt walking. And with this treadmill, we can assess with force plates in the treadmill, we can assess where the participants place their feet. And we calculate the step length asymmetry as a parameter of learning and a parameter of performance. And this asymmetry is measured as the difference between the left and right step length divided by its sum. And if you then look at the data over here, this short bit over here represents step length asymmetry during normal walking, so at tight belt speeds. And healthy humans will show a step length asymmetry of roughly 0, meaning that their left and right step lengths are equally long. However, in the early phase of split belt walking, so the first video you saw, there's a huge asymmetry in step length. And over the time course of this 10 minutes of adaptation, our group of healthy participants perfectly adapts back to baseline values and the step length has been adapted. But of course, we were interested in the adaptation of balance. So I'll show you this margin of stability as well, which was the spatial distance between the extrapolated center of mass and your base of support. Now, once again, here's some data from baseline walking, so normal walking. And you see that humans have enough for a margin of stability of about 1.5 centimeters. So apparently 1.5 centimeters is enough for us to feel safe during normal walking. But then when we speed up one of the belts, we go split belt walking, you see that there's a huge increase in these two lines. This black line represents the foot on the faster belt and the red line, the foot on the slower belt. And there's an increase to about 5 centimeters here and about 3 here. But over time, once again, as we saw in the video, our participants adapt their balance and the margin of stability decreases again. However, something interesting happened here, and of course you've already noticed it, because these margins of stability are quite asymmetric. So there's a larger margin of stability on one foot than in the other. And this caught our interest, and we investigated this. We found that this was related to step timing. What we found is that people, healthy young adults, when walking on the split belt treadmill, spend more time standing on one foot on the slow belt than on the other. So what they actually do is they place their whole center of mass over the foot on the slower belt, thereby unburdening the foot on the fast belt and increasing their margin of stability there. And in collaboration with the University of Southern California, we investigated this mechanism further because we thought this could explain walking asymmetries in people post-stroke, for instance. Because in these pathologies, you often see a walking asymmetry as well. Now, people with post-stroke hemiparesis often have one weaker side, so they have one impaired weakened leg and one more healthy unaffected side. And what you see is a similar phenomenon in which they spend more time standing on their healthy leg and less on their weakened leg. And based on this data, we now know that they may do this to increase their margin of stability on the weaker side as to make them more stable against sudden perturbations of their walking. So now we know that balance adapts to split belt walking, but we can turn the tables because our margins of stability, our balance adapts while we go split belt walking. But what happens to the adaptation when there's no longer a balance problem? So do you still adapt when you no longer have trouble to control your balance? And we can do this by increasing the margin of stability. So if we visualize the margin of stability in the picture on the left by the arrow, in normal walking without holding onto handrails, you have a small margin of stability, which should be enough. But if we get a group of participants to hold on to these handrails, they get a huge increase in their margin of stability because their base of support is no longer at their feet. No, now they have to hold on to the handrails, and for them to fall, they'd have to tip over these handrails. So they have a way larger margin of stability than the control group. And once again, we did a similar experiment. We have our healthy control group here struggling to walk on the split belt treadmill. And our handrail group this participant clearly lifts himself up from the treadmill a bit, holding on to the handrails, and has a lot less trouble walking on the split belt treadmill. And we can see this in the data as well. So this is the data you saw previously, a large asymmetry in the control group. So that's the video on the left and an adaptation. But our handrail group shows almost no asymmetry in the early phase and stays at around a baseline level. And what this shows is that the handrail holding reduces the perturbation that people experience by split belt walking. And this is very interesting because this is a phenomenon we actually see in daily life. If you have an elderly person who has trouble to walk and you give them a walker, in Dutch a rollator, as soon as you give them this walker, they walk a lot faster because the walker increases their base of support. Or another a similar example, which you can observe when you go to the supermarket. If you see someone who struggles to walk from the car to the supermarket, probably as soon as they grab a shopping cart, their base of support increases and they go through the supermarket a lot quicker than they go without the shopping cart. And this is an example of how increasing your margin of stability, giving you support, also increases your walking performance. So this is great. You say, well, if someone has trouble to control their balance, you just give them a walker and everything should be fine. However, I've got one more trick up my sleeve because there's a part of split belt walking and this whole paradigm that I haven't told you about yet. And that's a return to normal belt speeds. Because after our participants walk on the split belt treadmill for 10 minutes, so they've adapted their step lengths, we set the belts to regular speeds again. And our healthy participant in the videos on the left here, all of a sudden has to walk normal again. And this is what happens. So all of a sudden, after just 10 minutes of split belt walking, our participant struggles to make normal steps. The belts are going at the same speed, but she can't make the steps anymore. And for our participants, this is awfully confusing and they wonder what we did to them. Now, don't worry, in about 5 minutes, this effect will fade away and our participants will go home safely and without any trouble controlling their steps anymore. For us as researchers, this is very important because what this shows is that in this 10 minutes of split belt adaptation, people have actually learned to control their walking in a different way and recalibrated their steps. And we can say that learning took place here. So we're looking at motor learning in action in a very controlled and experimental setting. Now, if we look at the handrail holding group, we see that there's a slight hesitance in the first step, but there are no further after effects. They have no trouble walking normally again. And we can see this in the data as well, because I've added a line. We're looking at the control group here who weren't allowed to hold onto handrails. And you see that their step length asymmetry goes in the opposite direction. These are clear after effects of an adaptation. However, our handrail group shows no after effects, so no learning took place. And this is an important finding which has strong implications for clinical practice, because whereas we're normally eager to support our patients while learning them to walk, maybe we shouldn't let them go more freely, let them struggle a bit because they have to learn to control their balance during walking. And with that, I'd like to conclude in my thesis that we have shown that learning to walk is learning to control your balance, that in patient groups, asymmetric walking can actually be optimal for safe walking, and that balance assistance may increase walking performance at first, but in the long term may reduce learning. And with that, I'd like to thank my co-authors, promotion team, the Finley Lab at USC, all the sponsors of my previous and current research, and of course the KNG for letting me present here tonight. Thank you.
Okay, thank you very much, Tom. these were all very interesting, nicely presented summaries of the research that you have been doing. With that, you gave all the members all the information they need to go to the next important step, and that's being guided by George.
Okay. Thank you. That was an interesting row of speakers. So now, as a secretary of the Natuurkundige Genootschap, it's my pleasure and my duty to start the voting and explain it. All members of the Natuurkundige Genootschap received a mail with a specific code, and we now have a 10-minute break. And in the break, you can make your votes, and all the members can use their specific code. Was mentioned in the mail. Go to the website here already denoted, or you can use the app on your smartphone if you have downloaded that. You will then see the 4 candidates, and you have to rank them. So put your best presentation on the first, then come the second, the third, and the last one. And you will see a timer in the screen, and after 10 minutes we will announce the winner of this. So have a nice break, and we make your votings. I will bring up the end result by sharing my screen. And then Lou can take over, bring up. And here the winner is result by sharing my screen. And then Lou can take over, bring up. It's on the screen. The winner is result by sharing my screen. And then Lou can take over, bring up.
Yeah.
It's on the screen. The winner is result by sharing my screen. And then you can take over, bring up.
Okay, George, could you...
By sharing my screen.
Okay, George. George, could you take over with the screen because I cannot see it?
Okay, I thought I already presented the screen. Here it is. You see the screen?
No.
Okay.
Maybe you just read who is the winner,
okay.
because you can see the screen better than I can.
Okay.
So take over, please.
We closed the voting, and from the Mentimeter application, the ranking of the best Van Swinderen 2020 presentation is on the first place, Dr. Tom Burker. Second, Dr. Björn Krieten. Third, Ella Beckhuis. And the last, Dr. Herb Blanco. So the best presentation is Dr. Tom Burker.
Okay, Tom, great, congratulations. Great. Maybe you can just give a 1 minute response on what you think about this.
Yes, thank you all. Thanks to the KNG for letting me present here. And of course, congratulations to the other presenters. I thought it was a really interesting evening, and I see that this was quite a close call. Yeah, I already thanked all the co-authors and promoters. I'd like to do this again here. Of course, this research is more of a team effort rather than a one-man job. So I'd like to thank everyone involved before I forget anyone. And I really enjoyed to present here tonight again after a year with relatively few conferences and such. It was honestly an honor to present this research again. So thank you.
Okay, you're welcome. You're very welcome. So congratulations, and I guess it's interesting to see that we have such a close call here. So it was great to hear all of you present. And I guess the 2,500 euro, which is the prize winning, is the prize you are going to win, will be transferred to you. So you could give all the details to George Huytema, who is the secretary of our society. And in addition, you will also get a document that states that you are winning this Van Swinderen public prize, audience prize. So all the others, thank you very much. And also for you, we have 1,000 euro. And also for you, you will get a certificate. And also please send in your details to George Huytema, and he will take care of that. But we are not finished yet, because we have this other very special prize to present. I will ask Theo Elzinga to take over. Theo.
Okay, thank you, Lou. It is an honor for me to present the what is called in the program the expert prize, the jury prize, and that has been awarded to Björn Kriete. And I will quote a little bit from the jury report. It's a nicely structured summary which does present the story without referencing to the experimental chapter, but tells its own story. It avoids jargon and technobabble, and it combines both trying to answer fundamental questions on a societally very relevant topic. So we have awarded you an additional €1,000 for the jury, the expert prize.
Okay, congratulations.
Congratulations.
Then I take over, Theo, if it's okay with you. And I will make some closing remarks and then we finish with this session. Well, at the end of this meeting, I like to thank first all four contestants. You did a very fine job and we enjoyed your presentations a lot. Second, also great thanks to the 3 members of the jury. It is a lot of work reading all cum laude theses at the University in Groningen in the Faculty of Medical Sciences and of the Science and Engineering faculty. In fact, there were 19, and out of these 19, 4 were selected. So the 4 you have seen today. And to be clear, having a cum laude is already something very special because only 5% of all the PhD candidates get a cum laude when they defend their thesis. So that is really great. So you did a marvelous, good job. So the members of the jury, thank you very much. And also you all watching and joining us, and thank you for being with us. I hope you enjoyed it. And last but absolutely not least, I like to thank George Huytema, our secretary, and our technical team, Martijn ter Horst and Bert Kers, for their marvelous preparations to make this online event possible. I think it worked out fine, so thank you very much. Our next regular meeting will be in January. We had scheduled a lecture from Peter Kuipers-Munneke on January the 19th, but because the corona restrictions, this probably will change. We don't know yet how we will do this or when, so please check our website in January for further notification on this issue. This leaves me with wishing you a happy Christmas and a great new year. Stay safe, and I hope to see you soon in 2021. Thank you very much.